300 sailors drowned in under 4 minutes on the night of October 22, 1707, when the flagship HMS Association struck the rocks of the Scilly Isles and went down. 3 other ships followed her within the hour. The fleet's commander, Admiral Sir Cloudesley Shovel, had confidently plotted his position off the coast of Brittany. He was actually 90 miles off course, heading straight for England. Nearly 2,000 men died that night, not from enemy action, not from weather, but from not knowing where they were. This was not an unusual kind of catastrophe. It was Tuesday. Ships had been dying this way for 2 centuries, and everyone in maritime Europe knew why. Latitude you could determine. Longitude, you could not. And the difference between those 2 problems is one of the most elegant and infuriating asymmetries in the history of navigation. Latitude is a gift from geometry. The Earth tilts on its axis, the Sun sweeps predictably across the sky, and at any point on Earth you can measure the angle between the horizon and the noon sun, compare it against a table, and know exactly how far north or south of the equator you stand. The celestial machinery gives you that for free. Longitude is different. Longitude is not a geometric problem. It is a time problem. The Earth rotates 360 degrees in 24 hours, which means it rotates 15 degrees every hour. If you could compare the local time at your position, which you can determine from the sun, with the time at some fixed reference meridian at the same instant, the difference in hours multiplied by 15 gives you your degrees of longitude. Simple. Except that in 1707, there was no reliable way to carry a fixed reference time across an ocean. Pendulum clocks stopped working on heaving ships. Dead reckoning accumulated errors with every mile. And so navigators guessed, and ships wrecked, and people died. The political pressure finally snapped after Shovel's disaster. Parliament passed the Longitude Act in 1714, establishing the Board of Longitude and offering prize money on a sliding scale. £20,000, roughly equivalent to somewhere between £2 and £3 million in modern purchasing power, for any method that could determine longitude at sea to within half a degree. 10,000 for within a degree. 15,000 for within 2/3 of a degree. The board itself was stocked with heavyweight institutional authority, including the Astronomer Royal, members of the Royal Society, naval officers, and members of Parliament. It also attracted, as you might expect from a prize that large, a remarkable parade of cranks proposing solutions involving wounded dogs, magnetic poles, and stationary signal ships anchored at regular intervals across the Atlantic. The serious scientific establishment, however, had a solution in mind, and it was actually a genuinely good one. The moon moves against the background of fixed stars at a measurable rate, roughly half a degree per hour. If you knew, in advance, precisely where the moon should appear relative to specific stars at specific times at Greenwich, and you measured where it actually appeared from your position on the ship, the difference would tell you the time difference, and therefore your longitude. This is the lunar distance method, and it worked. The problem was that it required extremely accurate predictions of the moon's position, which required understanding the moon's notoriously complex motion, which had defeated Flamsteed, Newton, and Halley in turn. It also required, in practice, about 4 hours of meticulous calculation per observation, using logarithmic tables, after an already difficult series of measurements. Neville Maskelyne, who became Astronomer Royal in 1765, was the lunar distance method's most powerful advocate, and he was not a villain in this story, regardless of how he sometimes painted. He genuinely believed in his method's superiority, and he had real reasons to. He produced the Nautical Almanac starting in 1767, precomputing the lunar distance tables years in advance so navigators could cut those 4 hours of calculation down to 30 minutes. He was doing serious, important work. The fact that he was simultaneously the man who would stand in John Harrison's way does not make him a fool or a schemer. It makes him a scientist with institutional authority defending what he sincerely thought was the better answer. John Harrison was born in Yorkshire in 1693, the son of a carpenter, and taught himself clockmaking through a combination of obsessive observation and sheer mechanical inventiveness that has almost no parallel in the history of precision craft. He had no formal scientific education. He read his way into horology and then proceeded to solve problems that trained watchmakers had declared unsolvable. By the time he approached the Board of Longitude in 1730 with his proposal, he had already built wooden clocks of extraordinary accuracy, and had invented the grasshopper escapement, a nearly frictionless mechanism that eliminated the lubrication problems that plagued conventional escapements, since oil thickens and thins with temperature, degrading timekeeping in exactly the variable conditions a ship would face. Harrison's first sea clock, H1, was a strange and beautiful object, about the size of a small trunk, using paired weighted beams connected by springs to cancel out the effects of the ship's motion. It ran its 1736 sea trial and impressed observers, but Harrison was already dissatisfied with it. H2 followed, heavier and more refined. Harrison again declared it insufficient before it could be properly tested. H3 consumed 17 years of his life and introduced the bimetallic strip, two metals bonded together that expand at different rates with temperature change, bending in a way that automatically compensated for the thermal errors that temperature variation introduced. He also used, in H3, caged roller bearings, a device so ahead of its time that the bearing industry would not widely adopt the principle for another 100 years. Then he abandoned the whole approach. H4, completed in 1759, was about the size of a large pocket watch. It was a conceptual revolution. Instead of elaborate mechanical compensation for every source of error, Harrison had achieved sufficient precision through the refinement of a high-frequency oscillator and a new escapement design that made compensation largely unnecessary. In trials conducted partly by his son William in 1761 and 1762, H4 accumulated an error of less than 2 minutes over 81 days at sea, which was well within the prize threshold. The Board of Longitude acknowledged the result and then declined to pay the full prize. What followed was an institutional slow-motion obstruction that is well documented and makes uncomfortable reading. The board required Harrison to submit his mechanisms for examination. They required him to produce 2 more watches from scratch to prove the design was replicable. Maskelyne, who was by now Astronomer Royal and a board member, conducted a land-based test of H4 at the Royal Observatory that Harrison believed was done with deliberate carelessness. The goalposts moved every time Harrison cleared them. He did not receive the full prize until 1773, when he was 80 years old, and he received it only after a direct petition to King George III, who apparently found the whole situation sufficiently embarrassing to intervene. The figure most often forgotten in this story is Larcom Kendall. Kendall was a skilled London watchmaker commissioned by the board to produce a copy of H4, which became known as K1. The board wanted to test whether Harrison's design was actually replicable by other craftsmen, which was a reasonable institutional question even if the broader treatment of Harrison was not. K1 sailed on James Cook's second voyage from 1772 to 1775, and Cook's log entries about it are worth sitting with. He called it our never-failing guide and described it as our trusty friend. Over 3 years, across the Southern Ocean, through latitudes no European had navigated before, K1 performed. But here is the complicating detail that the simple clockmaker wins narrative tends to skip. The same voyage also used the lunar distance method simultaneously, with trained astronomers making observations and doing the calculations. Both methods were in use. Both methods provided navigational data. They were cross-checked against each other. In practice, at sea, the two approaches were not competitors. They were complementary. The question of why this whole solution took 60-odd years from the Longitude Act to wide adoption is worth taking seriously, because the answer is not incompetence or villainy. Harrison's mechanism required extraordinary craftsmanship to replicate. A competent watch could not reproduce it. A chronometer that could be manufactured at a scale useful to the Royal Navy required further refinements by makers like Thomas Earnshaw and John Arnold through the 1780s and 1790s, who developed designs that were accurate, robust, and manufacturable in numbers. The economics of craft production, the transmission of tacit knowledge through workshop traditions, the slow development of instrument making as an industrial practice, all of this was part of the solution, and none of it was solved by a single genius in a workshop. The conceptual insight that Harrison proved, though, has never stopped being used. Timekeeping and position finding are the same problem. The 24 atomic clocks aboard the GPS satellite constellation operate on exactly this principle, synchronized to nanosecond precision, transmitting time signals that your phone triangulates into a position accurate to a few meters. The method is pure Harrison: know the time precisely, and you know where you are. The 1707 disaster in the Scilly Isles and the 2023 navigation of a container ship through the South China Sea are separated by 3 centuries and united by one insight. But here is what the tidy version of this story leaves out. GPS signals can be spoofed. They can be jammed. They can fail. Maritime incidents attributed to navigation error still happen, and the question of how much redundancy modern systems require, how much we should rely on satellite timekeeping alone, and whether we have adequate backup methods, is genuinely open and genuinely contested among naval and aviation authorities right now. Harrison solved the longitude problem for his era by refusing to accept that the best available answer was good enough. So the question worth sitting with is this: when the system we have built on his foundation is disrupted, as it has been and will be again, do we have the equivalent of a nautical almanac waiting, or have we quietly forgotten that the backup was always part of what made the solution safe?